So today is our last lecture. Thursday, we have the coding portion of the midterm. And a week from today, at 8 o'clock, we have the paper final. There is no lab tomorrow because tomorrow is the first study day, so you've finished all of the lab sessions. So please make sure on Thursday that you bring your laptop because, Okay, so make sure bring your laptop because the coding portion is going to be on Code Assessor. If you don't have a laptop, we may have to just have you do the paper version, write it out by hand. Okay, so you'll get a one-page cheat sheet front and back. It covers recursion and linked data structures and trees. So I know that since the last midterm we've covered recursion and binary trees, but for the coding portion we did not cover linked structures on the last midterm. Therefore, there is one question about linked structures on the exam, and there's one question on recursion and trees on the exam. So there's two questions. Recursion one is one that involves both trees and recursion. There are practice coding questions that you can look at. If you go to the exams portion of the website, then it has exams from spring semester 2015, including coding ones, and they're up on the Code Assessor development site, so you can go and practice them there. The solutions are there, plus you can prep for the exam using some questions from Dr. Plank's old finals as well. And then for the final, same thing, you can use all of these different exams to prep for the final. The exam a week from today is going to cover primarily material from since the last midterm, so recursion and trees, but you do need to know about all the data structures we've talked about this semester, their running times, their average running times, their worst case running times, and when you use them. So it's kind of a review of that. So you have arrays that you have vectors, you have stacks that we've covered. We've covered queues. We've covered dequeues, double-ended queues. We've covered hash tables. We've covered lists. We have covered maps, sets. We've covered binary search trees. And we've covered AVL trees. Okay, so you need to know what are the performance characteristics for each of these types of data structures. So you need to know their best case, not best case, their average case and worst case running times in terms of BigO notation. And you need to know the situations where you would use them. Okay? So, for example, with arrays, You use them when you know the size of the data in advance, and you don't have to insert into the middle, where basically you can read all the data pretty much in at once, and you're adding stuff at the end of the array. You use vectors when you don't know the size of the data in advance, and you're pretty much reading it in and adding it to the end. Okay, whereas you use dequeues when you don't know the size in advance, but you might be adding to the front or back. And lists you would use when you don't know the size in advance, but you might be inserting and deleting in the middle. Okay, so you need to know the situations when you use these things. With hash tables, they're the most efficient for find, insert, and delete, unless you have to keep the data in sorted order, in which case you need to use a tree, like a binary search tree or AVL tree. Okay, if you need to keep the data in order, you use a binary search tree or an AVL tree. Now, maps and sets, they are simply an abstract data type for doing find, insert, and delete. It turns out that maps and sets can be implemented using hash tables or binary search trees or AVL trees. So sets and maps are more abstract data types that can be implemented using hash tables or trees. Now, in the C++ template library, how are they implemented? They're implemented using trees. Okay, and actually, I believe they're implemented using something called red-black trees, which we don't cover in this course. You probably will cover them in 302. So at any rate, you may be asked on the final to give the average or worst case for these data structures. You may be given various scenarios and asked which data structure should be used in that scenario. Both are important that you know that. So this is the one case where you are responsible for material that was presented earlier in the course. Because this is the big thing about this course. It was data structures and algorithms. So the big thing in this course was how do we organize data so that it can be efficiently manipulated? And this is what you need to be getting out of the course is this series of data structures. We went over a whole bunch of them, and you need to know the trade-offs. Okay, and the big three operations we considered this semester were insert, find, and delete. So being able to dynamically add or delete data from a set and then being able to efficiently find data in that set. Okay, so questions about that? Okay. So that's one, recursion is two, trees are three, and then the fourth thing, big O notation, which we're covering today, which we also covered a bit before the midterm. That will be also on the final exam. Okay? And you'll have an hour 15 minutes for it. So the exam will start at 8 on a week from Tuesday. We'll finish at 9:15. Okay, and then on Thursday, you'll have the entire class period. There'll be 2 problems. Okay. So, last big topic, Big O. So we already covered Big O a bit earlier in the semester. So you may remember the big thing this semester, one of the big things was being able to compare 2 different data structures, 2 different algorithms, and be able to determine which one is faster. Okay, so we're often faced with the question, given two algorithms, we'll call them A1 and A2. Which is faster for large n, where n is the size of the input? Okay, and big O notation gives us the means to compare two algorithms. It abstracts away all the clutter to focus simply on the biggest term in each algorithm. So let's say that the running time of A1 on n is n squared plus 10n plus 8, and the running time of TA of 2 on n is 1,000,000 n plus 20. Well, for small n, which is better? For small n, TA of 1, because that enormous constant means, in fact, that for n less than 1,000,000, TA of 1, or A of 1 is better. But for very large n, eventually the dominant term will show, and algorithm 2 for large n, in this case greater than 1,000,000, will be the preferred algorithm because order n is less than n squared. And in practice, you never get such exorbitant constants like 1,000,000. It would be maybe more like, say, 30 n plus 20. So eventually, that largest coefficient, or I'm sorry, the largest term, the largest polynomial, is the telling feature. So big O notation allows us to abstract away the clutter to focus on the largest term, and as n gets large, asymptotically, that biggest term determines how fast or how slow the algorithm is. And we're always going to prefer an algorithm that has the smaller polynomial term. Now, sometimes they have the same polynomial term, in which case we do fall back on caring about constants. But in this class, in many cases, there was definitely differences. Like a hash table takes order 1 average case time, and a balanced tree takes log n. Well, constant time is faster than log n. Log n is faster than order n, which is what it might take, for example, to search a list. So there's definitely differences between the algorithms. Now, one thing we did not discuss earlier is how we actually come up with these running times, with these functions t, which express the running time of the algorithm. So an important thing is being able to figure out, at least roughly approximate, what these running times are. Now, we're never going to get it exact, but basically, the idea is we need to count instructions. So we want to know the number of instructions that are going to be executed by each algorithm. Okay? So again, we have to abstract a bit because different CPUs run at different clock speeds. So two algorithms, they could run at different speeds on two different CPUs depending on those CPUs' peculiarities. So to kind of abstract away from that, we generally say that each instruction that gets executed takes a constant amount of time. We don't care how long that time is, whether it's a nanosecond, whether it's a microsecond, whether it's a millisecond. We just say that an instruction takes a 1 unit of time, whether it's a multiplication or a division or even a somewhat complicated expression, arithmetic expression. We're going to say it takes a constant amount of time. Okay, so we want to count up the number of instructions. And there are some simple rules for doing it. So we'll start by just looking at Dr. Planck's notes. So here he has a simple example where it's generating, it's just running from I0 to less than n, and it's generating kind of n randomish numbers between 1 and 1,000. Okay, so it's starting out with series of kind of setup statements. Then for I equals 0 to up to 1,000, it is just doing some things that tend to randomize f, and then it prints out f. Okay, now that print statement is commented out, but that's what this is doing. Okay, so anything that's a simple statement like count equals 0 or f equal 23.4, we just say is one instruction. So basically, without any other information, we count assignment statements as one instruction. But you can see here, these two aren't simple assignment statements. Okay? They both involve function calls. Okay, one is a to I, which of course I've told you is a bad thing to be using. And the other is calling the time function. So in these cases, we actually need to know how long the function takes. We need to know the number of instructions executed by the function. So we'd have to go to the function and count its number of instructions, and that would actually be the cost of this statement. Okay? So a to I, it turns out, and the time functions both take constant time. Okay, I just know that. So sometimes you know it, sometimes you'd have to do some research. But knowing that they take constant time, we would just still assign them 1 unit of time for our purposes. Okay, so basically sequential statements, actually let's do it here. So rules for counting instructions. Okay, so when we have sequential statements, we simply add their running times. So you figure out how much each of those statements take and you add their running times. Okay, the second thing is you get if then else. So in his program, he has if argc not equal to, he does a print and an exit, and otherwise he does nothing. So there's a couple ways to look at this. First of all, we could look at the best case. So in the best case, how many instructions do we have to execute? 1, which is the comparison. And the condition will be false, and therefore we won't have to do anything else. In the worst case, we'll have to execute 3 instructions: the comparison, the print, and the exit. When we count instructions, we're pessimistic. We assume the worst case. So when we count instructions, we say for an if-then-else, it is the max of the then and else clauses plus the cost of the comparison. You can't forget the cost of the comparison, because if it calls a function, that could be an expensive comparison. So it's the cost of the comparison plus the maximum of the then and the else. And if the else doesn't exist, then it is the cost of the comparison plus the cost of the then. Okay, so that's pretty simple. You've already seen the cost of a function. Okay, it is equal to the number of instructions executed by the function. Which brings us to the hardest one, which is loops. So in this program, we have a loop. And it actually isn't all that hard. A loop is equal to the number of iterations times the number of instructions per iteration. It makes sense. If there's 1,000 iterations and each iteration executes 3 instructions, there would be 3,000 total instructions executed. So we have to do 2 things with the loop. We have to figure out what is the number of iterations, and we have to figure out the number of instructions in the loop body. Okay, so here the number of iterations is pretty straightforward. It says for I equals 0, I less than n, I plus plus. So we're incrementing I 1 at a time, and it should be pretty clear that there are n iterations. So now we have to count the number of instructions in the loop body. Okay, well, count plus plus is 1. This assignment is 1. It's just a simple arithmetic operation. So is this division. So is this subtraction. And if the print were in there, we still count the print as a simple print. So there would be 5 instructions in the loop body. Plus, we can't ignore the comparison and the increment operations. So they're performed every loop body. So that's roughly 7 instructions per iteration. So roughly, this loop is costing us 7n instructions. Now, of course, that's a very rough, just a second, very rough approximation. Actually, we probably should add in this initialization statement. So that's really a +1 because it's done once. Not all of these instructions obviously take the same amount of time. The print is a fairly time-consuming operation, and we're probably taking more time in this instruction and in this instruction than in the division operation, but we don't worry about that because they're at heart constant time operations. They're irregardless of the size of n, they take the same amount of time. Okay, so for all practical purposes, we count them as just being 1 unit of instruction. Jacob.
So for a nested loop, assuming the case where you're like iterating through a matrix or something like that, we don't always know the matrix is going to be n by n.
Right.
Do you still consider that to be n?
Okay, we'll get to that. Okay, it's a good question. I'll get to that. So we'll just put that off for a moment. Okay, because we have to get to nested loops next, and then we have to get to where it's got two different sizes. Yes?
On like the exam and such, if you're having to look at the BigO for functions that we wouldn't necessarily know, like maybe A to I, would you be telling us that this one works for constant time?
Yes. If I gave you a function like A to I would say assume it's constant time. If you couldn't look at its code, I would tell you what the running time was. Yes. Okay. So, basically coming back to our thing here, the cost of a loop is equal to the number of iterations times the number of instructions per iteration. So with this, we actually now can compute the running time of this particular program. So we know that the if statement takes 3 because we have to assume the worst case. We know that each of these instructions take 1 unit of time, and the print at the end takes 1 unit of time. And those are all sequential. So it's basically 3. There's 4 here, 1 down here. So that's basically 3 plus 4 plus 1 is 8. And then the loop, we know, is 7n plus 1. So we have roughly 7n plus 8 plus 9. So it's roughly 7n plus 9. And again, this is a rough estimate, but close enough. Okay, so we say that t of n is equal to 7n plus 9. And now from that, we can get the big O running time is order n. What should be pretty clear from this is loops are the thing that are probably going to determine the running time of your program. Sequential statements generally are taking constant time. If statements are the maximum of the then and the else plus the comparison, but it's the loops that are driving your running time. So basically, it's going to be figuring out numbers of iterations. Now, it's not always this easy because sometimes you're going to get nested loops. Let's say you're doing the PGM lab where you're printing out all the pixels from a PGM file. There, it was something like 4 row equals, say, 0 to row minus 1. 4 column equals 0 to column minus 1. You might be saying print PGM R C. And the question is, okay, what's the running time of this loop? Well, it's not so easy because now we have nested loops. So the way we do this is we calculate the running times of the loops inside out. So we're going to start with the running time of the innermost loop. Okay, well, it runs for basically the number of iterations is equal to the number of columns. And there's essentially one print statement. Okay, plus there's some counting going on in comparison, so we know there's 2 if I wrote it out. So the inner loop takes roughly 3 times the number of columns. Now that we've got the inner loop, we can figure out the running time of the outer loop because we know now that that each loop body or each iteration of the outer loop takes 3 times columns instructions. So now that we've worked out how many iterations each, or how many instructions per iteration for the outer loop, we just have to figure out how many times the outer loop runs. Well, the outer loop runs however many number of rows there are. So the running time is rows times 3 times columns. So the total running time is 3 times rows times columns. So T of n is equal to 3 times rows times columns. Okay, well, you'll notice there's an issue here. What's the issue? Okay, what is T of 100? What's the issue? Why can't you tell me what T of 100 is? I've got a nice formula up there. There's no n on the right-hand side. So I got T of n equals 3 times rows times columns. Only problem is n is not on the right-hand side. So that's not particularly helpful to me. Okay, so we have to figure out in this case, what is n? Okay, well, there's a number of ways to look at this. One way is to say that n is the number of rows. So we could say n equals rows, and we could say m is equal to columns. If we say it that way, in fact, what we would say is that the running time is really a function of two variables, n and m. So we'd say it's 3 times n times m. And that sometimes happens where we have things like matrices and we don't know in advance what is the number of rows or the number of columns. So if the number of, we can't just say it's a function of the number of rows, because let's say there's only one row and there are 1,000,000 columns. We just can't say that it is really T of n equals n squared, because in this case, the number of columns is way larger than the number of rows. So sometimes we really don't know which is, we have T depending on more than one variable. And that's okay. That happens. Okay, so in this case, we might say that it's T n of m equals 3 times nm. So that might be one way to express it. Another way might be to say that n equals the number of pixels. Okay, and n in that case is equal to what? Rows times columns. So in that case, T of n becomes equal to what? 3n. So the choice of n, how we define n, is important. And there's two legitimate interpretations for n here. One is we say it's the number of pixels. The other is we say it's really rows and columns. And either way is legitimate, and you can make an argument for it. On an exam, I would actually tell you which way I wanted you to interpret it. Okay? But the really important, so there are two important points. One second, two important points here. First of all, what to do with nested loops. Okay, so with nested loops, we start from the innermost one and work our way out. Okay? Start with the innermost loop and work out toward the outermost loop. Okay, so that was one thing. The second thing is sometimes that the running time depends on more than one variable. Sometimes it depends on two variables. Okay, this happens also, let's say in the real world, that we want to take some data and organize it, and we also want to search it. Okay, so let's say that the size of the data set is n. And the number of searches is equal to m. Okay? Well, we don't know in advance what the size of the data set is and what the number of searches are. So we don't know which of those two variables is bigger. Okay? So we might know that we're going to insert into a tree. So we know that insert in a tree is order log n. We also know that find in a tree is order log n. So we know that we're going to do n inserts because there's n items in the set. So n inserts equals n log n time. And we know that there's m finds. So that's m times what? There's m finds on a data set of size n. It's log n because the data set is log n. So the time of our program is, again, actually a function of both n and m. It's n plus m times log n. And we can't say in advance which of those two is bigger. So we have to include both factors there. So in this case, when we said, what is the big O running time? We would actually say it was n, we'd actually say it's big O of n and m because it is, in this case, a function of 2. So we say the big O running time, the big O running time in this case is of n and m, and it's n plus m log times log n. Oh, I don't have enough room. So in this case, we'd say it's actually O of n comma m, and it's actually n plus m times log n. So sometimes our running times are a function of 2 variables. We could even have 3. If I had deletes as a third operation here, I would have to add in the number of deletes. Turns out that's pretty uncommon to have to do that to go that far. Usually we can get away with just looking at one variable. Sometimes we have to look at 2. Jacob, take you first.
Is it ever beneficial to assume our pessimism as programmers for the sake of using the matrix, for example, just assume the worst case where you do have an n by n matrix and just call it n squared?
No, that's a bad idea. Because, so the question was, should we sometimes just be as pessimistic as possible and just assume that it's going to be n is the, it's going to be n. The problem is you don't know which is bigger, n or m. So you can't say it's n squared because n might be much less than m. So if you're trying to be pessimistic, I suppose you could say it's max of n squared and m squared, but then you're not really putting as tight a lid on it as you could. Okay, so that's why. Yes?
So why the n insert is n log n? Even for your first insertion, you're only have one data.
Okay, good question. So the question was, why is it n log n? Because really the first insertion doesn't take log n time. The first insertion is constant time. The second insertion essentially is constant time too. Okay? But if we add them all up, it's going to turn out that it's going to come down to, so if you were to add them up, it would be something like 1 plus 2 plus dot 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 plus eventually you get up to log n. And if you sum them all up, it's going to end up still being on the order of log n. It's like if you do this, 1 plus 2, it's not exactly the same, plus 3, plus dot dot dot, plus n minus 1. Okay, so the first operation was constant time. The second operation only took 2. So if t of n is equal to this, what is it? Does anyone remember the formula? This one has a formula. Yep, or n, it's really n times n plus 1 over 2 is what that is equal to, which is n squared over 2 plus n over 2. So even though it is, the first few operations are constant time, when you get done summing it, the closed form expression is still n squared. And it's it's not exactly the same over here, but it's in the same thing that once you get through summing them all up, you're back at log 2 and divide it by some constant. So the constant is irrelevant. We throw it out. We're back to the log n term. That's why. You're welcome. Okay. So questions about that? So that certainly happens. You get stuff that looks like, you might have something like, say, 4i equals 0, I less than n, I plus plus. And then the inner loop is, say, 4j equal 0, j less than I, j plus plus. And you're doing something. Okay, now you do the inner loop. So each iteration of the inner loop is actually I is the number of iterations, we'll say, times some constant c. So the number of, let's just say it was 3 to make it concrete. So maybe it's 3i. Okay, well, we come to the outer loop, so we now know that this is 3i, and you're thinking, geez, I know that the outer loop runs n iterations, but unfortunately, that inner one is 3i, and that's varying based on the value of I. So what you really have, in this case, is when I is 0, it's 0. When it's 1, it's 3. When it's 2, it's 6, plus 9, up to 3 times n. So what it really is 3 times 0 plus 1 plus 2 plus 3 plus dot dot dot. Actually, the last one is n minus 1. Okay, but we know that this thing is really n times n minus 1 over 2. So eventually we would come to 3 halves times n squared minus n. So sometimes you have to do a little more work to get to it. Okay? But, so in 311, We don't get to it, but eventually you get to 311, CS 311, which talks about discrete math, and you're going to learn some of these equations because they become important when you're counting the number of instructions that get executed. Okay? If you remember, selection sort is actually kind of like this one, except that it's for j equal I plus 1, j less than n. And what you're doing in selection sort is you're trying to find, in the inner loop, the smallest value in the remaining part of the array. So in fact, that kind of loop does come up where it's a function of I. But in this case, it still ends up the whole thing being order n squared. Okay? And just to give you a taste, I'm not going to expect you to know it for the exam, but recursion can give you a bit of an issue. Okay, so let's say that we have some recursive thing where what it does is it breaks the problem in two. So let's say we have an array. We want to sort it. Let's say what we do is we break the array in two. So we sort, our algorithm is sort first half, sort second half, and then merge the two halves. It's called merge sort. Okay, well that's a recursive algorithm where the time is actually 2 times t of n divided by 2 because those two sorts are sorting half of the array plus the time to merge, which is probably on the order of n. Okay, so this is probably going to be plus n because it's probably going to take about n instructions to merge the two halves. But this is what is called a recurrence relation. And we're not going to discuss it in this class. Again, you'll get to them in CS 311, how you solve these. Turns out the solution to this is n log n. If you were to solve it, you get n log n. But that's not for this class. But at any rate, that is something that comes up where with recursion, you end up with something on the right-hand side that is still a function of t. And you have to solve it. So it's called a recurrence relation. Okay, again, we won't consider it further in this class. Okay. Questions? Yes.
I have a question about this program.
Okay.
At the top, with that if statement, you said consider worst case scenario, which would be 3. But if it's worst case scenario, the program exits. So.
Right. So then that's more semantic knowledge. So in fact, that's a good point. So the question is, if this if condition is true, then in fact the program exits. So in this case, we would actually assume that in some sense, the worst case is that it continues to run, right? So in that case, we actually would count this as one instruction because if it were to execute, we would exit. But generally, this exit instruction isn't in there. So this wasn't the greatest example of an if statement. Usually, we're not exiting the program because of it. But that's a great point. If there is that exit statement in there, then the worst case is actually that the if statement is false. We continue to execute, and therefore the worst case is one instruction executes. That's a great case. On an exam, that would be a trick question. I would not throw something like that at you on an exam. Okay. Also, sometimes we are more interested in average case. So usually when we calculate running times, we calculate worst case. But for example, with hash tables, in the worst case, what is a hash table? Order n. In the worst case, a hash table, everything hashes to the same bucket. So if we were really being incredibly pessimistic with hash tables, we would have to assume that everything hashed to the same bucket, and we would end up with order n, and we would never use it. We would say, well, hash tables are worse than trees. So in some cases, we actually stop and say, okay, how likely is the worst case? And with hash tables, we say, in fact, highly unlikely. So with hash tables, we also care about the so-called average case. And in the average case, the numbers or the keys distribute evenly to the buckets, and we end up with constant time. So we also sometimes will worry about average case time. Most of the time, we worry just about worst case. Sometimes we worry about average case. So with hash tables, we worry about average case times. Okay, what is another situation, another data structure where we made a distinction? So going back, so the preparation for the exam. One of these data structures also has a distinction between average case and worst case times. Trees, binary search trees in particular. So in the average case where the keys come in random order, binary search trees are log n for find, insert, and delete. What is the worst case for binary search trees? O of n. And when does that happen? When the data comes in sorted. Okay? So there again, the worst case for binary search trees is different than average case. And it's important to know the distinction. Okay. Other questions about this program? One quick thing, we don't count variable declarations unless there's an initialization. If there's an initialization, we count it as an instruction executed. Or if the constructor is called, we count the time of the constructor. But if it's simply allocating memory, which is all that is happening with each of these declarations, we don't count them. So declarations don't count unless there is an initialization. So if I said long, t of 0 equals 0, now that counts as an instruction because it's being given a value. So we only count the declaration if it's being initialized. Okay? Or let's say I had an object stack S and I called it with the parameter 10. Now I need to know the cost of that constructor. Okay? Because that's what it costs to initialize that particular stack variable. Okay, so moving on. We already went over the differences. Again, I want to point out, though, that log n is much, much less than n. So on this axis here, this pink line is log n. Here is n. Here is n log n. You're not even seeing n squared here. It's so bad. Actually, you do. It's going straight up. So log n is great. It goes up very, very slowly. Okay, because it's the opposite of 2 to the n. 2 to the n grows incredibly fast. Okay, remember my example with the king and the peasant? Peasant saying 1 grain on the first checkerboard square, 2 on the next one, and the king was broke by the time he got to 64 because 2 to the 64 is an astronomically big number. Well, conversely, log 2 of 2 to the 64 is 64. Okay, 2 to the 64 is an enormous number. But log 2 of 2 to the 64 is only 64. So just like exponentiation grows very rapidly, log 2 grows just as slowly, grows incredibly slowly. Okay? So log n of 1,000 is 10, of 1,000,000 is only 20, of 1,000,000,000 is 30, of 1,000,000,000, what do you think it is for 1,000,000,000,000? It's 40. A zillion is 50. It just doesn't grow very rapidly. Log n is a very, very fine running time. Okay, so we love log n. In fact, n log n, while here he's showing it as being much worse than n, it's not in the long run all that much worse because for practical purposes, log n is almost constant. Not quite, but fairly close. So n log n is actually not that much worse than order n. We call it log linear. You'll often hear the word for n log n called log linear because it's very close to linear. Log grows so slowly, it's almost like it's a constant. Not quite, that's why it's called log linear, to distinguish it from straight linear. But log linear is a pretty good running time too. But n squared is getting out of control, starting to get out of control. We still use n squared algorithms a lot. Those PGM files effectively are n by m, so they are, in fact, n squared algorithms. And as cameras get bigger with their resolution, you get like 1,000 by 1,000 versus 2,000 by 2,000. In fact, the number of pixels handled by photo processing algorithms is growing at a rate of n squared. Same thing, the number of pixels on those big screen TVs, they're growing at n squared rate. Okay. So, actually, did he not show it here? Yes, there it is. Okay, so what constitutes, so looking at each of these, we look at first this one. We have 2 sequential loops. When loops are sequential, that's different than being nested. When loops are sequential, we go back to our first rule, which is that for sequential statements, we add their running times. So here, we actually add the running times of the 2 loops. So this is actually roughly, they're the same loop, and there's 4 instructions plus 2. It's roughly 6n plus 6n, or 12n. For this log one, why is it log? Well, look right there. Even though the loop is I equal 1, I less than equal to n, I is being doubled at each step. When we double I at each step, it reaches n in log n time. There's only log n iterations here. Because when you double I at each step, it requires only log 2 n doublings to get up to n. Down here, we have nested loops. So we work out the inner loop first. Well, the inner loop, it has that doubling going on, so it's log 2n iterations times however many instructions, 1, 2, 3, 4, 5, 6, so times 6. And then the outer loop executes n times, there's n iterations. So the outer loop is n iterations. So we end up with n log 2 of n plus, oh, that's it, 6n log 2 of n for that one. And this one is just straight. This one, the inner loop executes n iterations times 6 instructions. The outer loop, right there, this loop, also n iterations. So it ends up with 6n squared. So I would expect you to do roughly this on an exam, but more likely I'm just asking you to come up with the biggest term. Charles, start with you.
So when you do the outer for loop, I see you ignoring the I plus plus, the I less than n. Do you just
Actually, I'm not. Oh, yeah, I am. So Charles said I noticed here that I was ignoring the outer, I was ignoring the counting. I really shouldn't. So if I was really being strict about my accounting, I would say the inner loop actually is 6n plus 2 for these two instructions. And then I'd be multiplying it by n. So you can see I am playing fast and loose with the, but I'm playing fast and loose because I know that those are constants. Yes? So basically, just before I get off of this, for a test, I just expect you to be able to come up with the biggest term, which would be n squared for this one. It would be n log n for this one, n for this one, and log n for this one. That's what I would expect on an exam. As you can see, getting into the fine counting, everyone's going to count a little differently, and I just wouldn't want to have to deal with all the variations you would come up with. Okay, I will. Where do you want me to go to?
It's fine, it's right here. Where it says I times equals 2, if that would say 4, would that be log 4n?
Yes, very good.
We still write it as log n.
Yes. So the question is, if it was I times equal 4, it really becomes log 4n. But the question is, do we just still write it as log n? And the answer is yes, because it's only a difference of a constant factor. Okay, in fact, Dr. Planck has something about that. There it is. So he says order log n, and we don't include the 2. He says now you may ask what base. It actually doesn't matter because that particular equality holds. So log base b of c is equal to log base a of c divided by log base a of b. So regardless of, so log base b of c and log base a of c differ by at most a constant, and therefore we don't care, because all we care about with big O notation is the biggest term, the polynomial term. So because logs differ by a constant, we don't care. Okay, so couple wonky things now. There are two other things. So we had said that, actually that's not what I want, that's what I want. With big O, we say that T of n is big O f of n if there exists a constant C0 and an X0 such that for all n greater than X0, C0 times f of n is greater than T of n. So what big O is an upper bound on T of n. What we're really saying is that T of n looks like this, and it's big O. If it's big O of f of n, then at some point x0 there's this crossing, and that big O f of n becomes bigger than T of n for all n greater than x0. So it's an upper bound. Now, it's not a strict upper bound. So for example, if I have T of n equals 5, T of n not only is order, we said order 1 for constant, it's also order n. It's also order n squared, right? Because n, all I have to do is choose for n, if I choose x of 0 equals 6 and c equal 1, then n is greater than 5 for all n greater than or equal to 6, and therefore that T of n is order n. So it's not a strict upper bound, it's just an upper bound. So what we really want is a strict upper bound, not a loose upper bound. So in this case, we really want to say it's order 1 because that's the strictest upper bound. So mathematicians come up with a couple other things for it. One is a lower bound, which is called omega g of n. So omega g of n is going to be a lower bound on T of n, just like O of n is a upper bound. Okay, so we're going to say that omega T of n is omega g of n if there exists constant c in x0 such that for all n greater than x0, T of n is greater than, C times T of n is greater than G of n. So that puts a, let me make sure that jives with his definition. Yes, that's going to be my definition of it. So C times T of n is greater than G of n. So that's putting a lower bound on T of n. And finally, we say that we have theta. So we say that T of n is theta f of n if, and only if, T of n is both order f of n and omega f of n. That means that the upper and lower bound are the same. So theta is actually what we're after, because theta is giving us a strict upper bound. But for some reason, computer scientists have adopted big O to mean theta. So when you hear computer scientists say that an algorithm is big O of 1, what they really mean is that it's big theta of 1. So you just have to get used to the fact that computer scientists, for whatever reasons, have conflated the meaning of big O and theta. So if we're being mathematically precise, big O is only a loose upper bound on T of n. It's not a strict upper bound. Omega is a lower bound. And again, it's not a strict lower bound. It's simply a lower bound on T of n. And theta is a strict bound. It's saying that it is both less than that and greater than that, therefore it is that. It's not saying both, it's basically saying that there's constants such that T of n is less than some constant C1 times f of n, but is greater than some other constant f of n. Okay. And actually, I should have changed this definition. I realized the constant should be over here for C. You should put the constant so that T of n is greater than C of n. That's what I really wanted. So the constant really needed to go on the right side. Okay, so this is what theta is really all about. And again, as computer scientists, we don't say theta, we say big O. And by big O, we actually mean theta. It's the strictest, it's the tightest upper bound on the running time. So even though T of n 5 is big O of 1, big O of n, and big O n squared, we say it's big O of 1 because that's the strictest upper bound on it. Okay? So I will see you all Thursday. Make sure you do those code assessor practice problems, and good luck with the studying and the rest of your exams.